gravitational force. Okay, so we're going to talk about the motion for the satellites and the planets. These things, of course, they are some kind of circular motion. Okay, I mean, not perfect circle, maybe oval shape, but they are also in the part of the rotation and circular motion. Okay, for that we need first learn how to calculate the gravitational force in general. Previously, we talked about the weight. Sometimes we refer it to as the gravitational force. But precisely speaking, weight is a special case of more general gravitational force. Okay? The general gravitational force is calculated by the Newton's law of gravitation. Okay. It says that if you have two objects, one with mass, either you can call it m1, m2, or capital M, small m. Okay. Anyway, you have two objects with different mass, and the distance between the two objects, okay, measured from the center of mass, is called r. So we know that due to the mass, the two objects will attract with each other. Okay, so m2 attracts m1 with a force, let's call it F1. And F1 attracts F1 with a force F2. Okay. The two forces, they are in the opposite direction. Okay? They are attracted with each other. According to the Newton's third law, they should have the same magnitude because they are action and reaction. If M1 attracts M2, and then the M2 will have some reaction, attract M1. Okay, so they are action and reaction. So they should have the same magnitude. How can we calculate the magnitude for F1 and F2? Both of them will be given by this equation. G multiplied by the product of two masses divided by r squared. Okay? G is called the universal gravitational constant. 6.67 times 10 to the power of negative 11. And M1, M2, or capital M multiplied by small m, that's the product of the two masses. R squared, okay, is the distance squared. Okay. And here, the magnitude, of course, calculated by that. The direction, please note that the direction cannot be directly seen from the equation. You have to determine it by yourself. This is a notation which says it's in the radius direction. So it's, but it doesn't say much since basically you need to analyze it from your graph. Like if you have two masses, if you are talking about the gravitational force acted on M1, so the force is to the right. Okay, it's attracted by M2. If you are talking about the force acted on M2, so it's to the left. Okay. Gravitational force, it can only be attraction, so you can determine the direction by looking at the position of the two masses. Okay, so the equation here is quite straightforward, and so that's how we calculate the general gravitational force. Now, what is weight? Okay, so this is calculated by G, capital M, small m over r squared. We know that we usually calculate weight with this equation, simple equation mg, right? Okay, this special case is only valid when you're talking about something very close to the Earth's surface. Okay. If you just try to calculate this, the gravitational force acted on this object. Okay, what happens is that if you do this calculation, let's start with the general equation, okay, and then derive the spatial equation. So Fg in general should be capital G, capital M, small m over r squared. Okay. So in this case, that's the attraction between this person and the Earth. Okay. So small m is the mass of this person. And the capital M is the mass of the Earth. Okay. So it can have G, ME, M. Here ME is the mass of the Earth, it's a constant. Now, the distance between the two objects should be the distance from the body center to the Earth center. It's approximately the radius of the Earth, right? Okay, because the distance from your body center to the ground is really small compared with the radius of the Earth. So you can think about it's nothing. So this R is actually the radius of the Earth. Now you can see G is the universal gravitational constant. This is the mass of the Earth, constant. This is the radius of the Earth, constant. So together, this is a constant. Okay? We can calculate the number, okay, the combination of these constants. You can do the calculation by yourself. You will see that it will give you 9.8, okay, meter per second squared. So since it's an important constant, so why don't we just give it a name? We will give it a name we call this small g, gravitational constant. That's why we have the Fg in this spatial situation equals to mass multiplied by g. Okay, any question here? So in fact, g is a derived constant. It's a combination of these constants from the general rule. And so, capital G, please note that capital G is called the universal gravitational constant. Small g is called gravitational constant. The difference is that this is universal, this is not. Okay. If you are going to calculate, say, the gravitational constant at the moon surface, okay, then you can see what you are going to do is that then Fg should be again the same universal general equation. But now when you try to calculate this gravitational force, it will be G multiplied by the mass of the moon, okay, multiplied by the body mass, divided by the radius of the moon, okay. And then you can still try to define a g, small g, in terms of this. But in this case, it will be a different value, right? This one will not give you 9.8. It will give you some other number. And then that will be the gravitational constant at the moon surface. This is the gravitational constant at the Earth's surface. So it depends on the location, okay, and which capital M you are talking about. Okay. So in fact, you can try to calculate the small g and any different position in the universe. Okay, it's calculable. And that will give you the distribution, the different value of g at different location. It actually give you the concept of gravitational field. Okay. You probably heard about this word, gravitational field. What do we mean by the gravitational field? It's just the value of g at different position. Like if you try to calculate gravitational field around the Earth's surface, so 9.8 at the Earth's surface, maybe 9.7 a little bit above it, 9.6 above it. So there's some distribution of this gravitational force. Okay, and precisely speaking, that means your weight does change at different location. Okay, like if your weight is 100 Newton, okay, cannot be 100 Newton. That means only 10 kilogram. Okay, should be I guess 800 Newton or something like that. So and here, if your weight W equals 800 Newton here, Then if you measure the weight at different position, like here, maybe just 400 Newton here. Okay, it's very far away from the Earth's surface because at that part G maybe just will be smaller than 9.8 at that point. Okay. So the same mass, when you calculate M multiplied by G, will give you the smaller weight. Okay? Any question here? That's a gravitational force. Okay. So one of the questions is here. Of course, we can calculate with Newton's law of gravitation. We can calculate the weight at the surface. We can also calculate the weight or the gravitational force at any place above Earth's surface. You can just use a different radius for the calculation, right? So there's no problem. But if I ask you a problem, suppose I'm here. Okay, I can make a hole here. If I'm standing here, how to calculate the weight or the gravitational force acted on my body at that position? Okay, the question is that in this case you can see the gravitational force from the Earth now is quite different that I'm inside of the Earth. So this part, like okay, you can see like this part will attract me downward, but this part will attract me upward. Right? So it's quite difficult to calculate in this case. But if you use an integral and other devices to do some calculation, it will show that the result can be summarized in the so-called Schell's theorem. Okay, a uniform shell of the matter attracts particle that is outside the shell as if all the shell's mass were concentrated at its center. Okay. So, if I try to calculate, okay, first, before we do that, okay, let's first do this. In fact, it says that, let's start from here. If you have two objects, very small objects, we calculate it by just the gravitational, the Newton's law. So the mass multiplied by mass and the radius. And if you have a quite large object and small object here, just as this one, okay, here we need to clarify that. One thing is that we think that the radius can be taken from this center to this center, even they actually touch each other. Okay. The reason is that we can, for this object, the Earth, we can try to concentrate all the masses into the center of mass. Okay. So we can replace the big sphere by a small particle with all the masses concentrated here. Okay. So that's a Schell's theorem. Okay. That extends this kind of configuration to this kind of configuration. And now, if we try to calculate this one, what happens is that we can divide it. And so you have this part and this part, right? And it can show that the mass from this part, the gravitational force, will cancel each other. So then, to calculate, you only need to calculate the inside part, the gravitational force from inside part. So you are going to have a smaller Earth here, part of the whole Earth, and then the radius is from here to the center. So this part, they will cancel each other. Only this part gives you the net effect. And then you cite the Newton's law of the gravitational force with the new mass and new radius. Okay? Any question here? So that means also when you are inside of the Earth, the G will be smaller than 9.8. Okay, because now you only get the attraction from part of the Earth. So what happens is that if you consider this is Earth, you consider the radius. If you try to calculate gravitational force, then inside of it, so kind of like this. Okay, so at the Earth's surface, you get the largest gravitational force. If you go away from the Earth, or you go inside of the Earth, you will have the smaller gravitational force. Okay. Away from the Earth, of course, due to the radius change, okay, R increases, that decreases the gravitational force. If you go inside of the Earth, that's due to the mass decreases. Okay, because only part of the mass are attracting you. Okay, so